Hey guys, it's Miss Butler. I have a video on introduction to bonding. We're going to focus mostly on ionic bonding and drawing Lewis structures. To really understand ionic bonding, you need to understand ions. So one vocab word that I need you guys to know is called the octet rule, and it's that elements will gain or lose or share electrons to achieve a full outer shell of 8. So remember, the outer shell is where the valence electrons are. We want to have 8, which we call a complete or a full octet. So each element wants to feel like the noble gases, right? The noble gases have that full outer shell. In this unit, we are going to focus on elements gaining and losing electrons. We will talk about sharing electrons next unit. But why would an element want to gain or lose electrons? Why would they give away what they have, or why would they beg for more? The real reason elements will do this is stability. If they gain or lose electrons and have that full outer shell, they will feel more stable. So here's an example. Sodium, Na, is in group 1, so it's in that first column on the periodic table. It's right here. And it has one outermost electron, one valence electron. If it loses that electron, it will have a full shell. I know that sounds kind of weird, but if you look, let me grab my highlighter. Here is the one outer ring. You see the one electron right here. If it loses that electron, that outside ring is now empty, and we go now to this inner ring, this second ring, which has a full 8. So for sodium, it is easy for it to lose one electron. When it loses an electron, remember, electrons are negatively charged, so if it gets rid of a negative charge, it will form a positive 1 ion, and positive ions are called cations, right? Cations have paws, cats meow. So sodium will form a +1 cation when it loses its one outermost electron. All right, so remember, electrons are negative, so if an element is gaining electrons to fill that outer ring, it will have a negative charge, and if it loses electrons to fill that outer ring or to get down to that inside full ring, it will have a positive charge. Same idea right here. So here is an example. Chlorine, here's a Lewis structure of chlorine. It has 7 valence electrons. It's going to gain an electron. You see that extra electron right down here, and it has a -1 charge. The example we just talked about, we had neutral sodium. It loses the electron, and we get sodium plus. Don't worry about these guys right there. All right, what ions will the following elements form? So my strategy with this is we're trying to get to the magic number 0 or 8, whatever is closest. I say 0, again, no one wants to have an empty outer ring, but if I am something like the sodium example and I lose the one electron in my outer ring, we will go to an inside ring that is full. So mentally, you're thinking about, how do I get to 0 or 8, and you're going to go the fastest way, the least amount of work. So first, let's actually do the number of valence electrons. So lithium is in the first column on the periodic table. He has 1. Magnesium is in the second group. He has 2. Boron is in the third group. He has 3. Oxygen is in the, if you skip all those transition metals, in the 6. He has 6 valence. Fluorine has 7, and argon has 8. Okay, so now we want to do the charges. What ions? That's a charge. So lithium, is it faster for lithium to get to 0 or to 8? Well, 1 is closer to 0. So what it's going to do is it's going to lose 1 electron. If we lose 1 electron, remember, if we lose, we actually form a positive charge. It feels backwards, but it's because electrons are negative, so we'll form a +1 charge. Okay, magnesium, 2 is closer to 0 or 8. It's closer to 0, so it's going to lose 2 electrons and form a +2 charge. Boron is 3 closer to 0 or 8. It's closer to 0, so it's going to lose those 3 outermost electrons, form a +3. Now let's look at oxygen. Is 6 valence electrons closer to 0 or 8? So essentially, oxygen can either kick out 6 electrons or it can find 2 more. What's less work? Finding 2 more. It's going to gain 2. So that will make a -2 charge, because remember, each electron that it gains is a minus. This guy will gain 1 electron, because 7 is just 1 away from 8, so it'll be a -1. And this one will form no charge. Remember, the noble gases don't want to give, they don't want to get, they don't want to share, they don't want to do anything, because he is already happy with his 8. We'll look at this in class, but alkali metals are in that first group on the periodic table, and they have the ability to get rid of one electron and form a positive one charge. That's pretty easy to do, so it makes them very reactive. Basically, they're looking for anyone and anything nearby it to give away that electron. So anything that they come in contact with, air, water, whatever it might be, they're trying to dump off that extra electron, which makes them very reactive. I got a little video, don't worry about watching it now, we'll watch it in class, and then I have a cool demo to show you guys later. So hopefully we did this in class, but if you missed it, just like we labeled the valence electrons, we were able to label the common charges. So we have +1, this whole column is +2. We put variable valence and charge +3, plus or -4, right? Because they could give away 4 or gain 4, -3, -2, -1, and 0. A couple that I would like you to write down, lead is, if you want to make a note, I know it says +2 and it's in the plus or -4 column, and maybe even tin. Let's label those two as variable. They should be plus or -4, but because they're so big, they actually kind of break the patterns. And then I would also like you to label the following. Aluminum specifically as +3. I know it's in the +3 column, but just do it. Zinc as +2, cadmium as +2, and Ag as +. If you notice, some of these guys in the middle have multiple possible charges. We'll talk about those in a second. But if you could, in the boxes for those blue elements, label them, and then in the boxes for the yellow, label as variable charge. Make a note for yourself. That will help you later this semester. So the transition metals that block on the middle of the periodic table, we wrote down earlier this year that they have variable valence, meaning it kind of can change depending on the situation, which means they have the ability to make more than one charge. Usually metals are going to, I'll say instead of give, I'll say lose electrons. So they're always going to have some sort of positive charge, but we don't know positive what. So in order to know this, like all of the other columns on the periodic table, I can figure out the charge by looking. You can't tell by looking just at iron and where it is. So what we do to make it obvious is we put Roman numerals behind the element. This tells me the number of valence electrons, and it also tells me the positive charge. So this is iron +2, it has 2 valence. This is iron +3, 3 valence, gold 1, gold 3. So if you don't know your Roman numerals, that's 1, 2, 3. IV is 4, V is 5, and if we ever get that far, VI is 6. That's all you really need to know in terms of Roman numerals. All right, so here's where we get into the Lewis structures. So draw the Lewis structure for sodium. Sodium is in the first column. It has 1 valence electron. Chlorine is in the 7th group, or all the way over if you're counting just straight up 17th group. All the way, it's a halogen, so all the way near the noble gases. So sodium wants to lose this 1 electron. Right? Chlorine wants to gain 1 electron. Well, what can they do to benefit both? What if sodium gave its electron to chlorine? Right? Wouldn't that make sodium happy? It wants to get rid of 1. Wouldn't that make chlorine happy? It wants to gain 1. That's how we can benefit both. That is what ionic bonding is a transfer when one element gives away the electron to another element. All right, here's some general properties, and we will actually spend a lot of time doing naming, but here's some basics. We always put the metal or the positive charge first and the non-metal second. So remember on your periodic table, we have that metalloid staircase. These are all the metals. These are the non-metals, and don't forget hydrogen is a weird non-metal. Okay, so potassium bromide, magnesium oxide, what I noticed is the endings change of the non-metals. So really, this is just potassium bonded with bromine. This is just magnesium bonded with oxygen, but don't let those ides mess you up. up. We'll focus on that later this unit. Some properties that you need to know, some behaviors of ionic compounds. They will dissolve easily in water and other polar solvents. Really, mostly we care about water. So I put something like potassium bromide in water, it will dissolve. In solution, so when they are dissolved, it conducts electricity. And when they're at room temperature, they're usually crystal solids and they have high melting points. It takes a lot of energy to get them to melt. Here's a nice little joke if you want to read. We got all the positive dudes inside and all the negative non-metals. Ha ha ha. Okay, so for ionic Lewis structures, we are going to show electron movement, so the transfer, and then we are going to do a final structure as well. So I'll do the first one, or the first couple with you guys. So the first one is sodium chloride. So we know we're going to have sodium and chlorine. First, I draw the Lewis structure for sodium. It has 1. Then I draw chlorine. Chlorine has 7. So that step is not really changing. You know how to draw these Lewis structures. Then I want to show the transfer. So what I see is that sodium wants to give that electron to the empty spot. So I draw an arrow from the dot on sodium to the empty location on chlorine. That's kind of my before picture. If you want to use a big arrow to kind of separate before with the transfer and after, you can. And then what we do, and these are going to look a little funky, but basically what's happening here is when sodium gives away its electron, I'm not going to put any dots on it anymore, it's naked, it's going to form a +1 charge, right? So it's donating this electron, but it forms a positive. Chlorine, and I always put the non-metal in brackets, had 7 dots, and now it has that 8th dot from sodium. So I'm going to draw chlorine with all 8 dots, and when it gains that electron, it's a -1. So this isn't just a sodium, here you go, and chlorine, thank you, and they go their separate ways. What happens is as soon as sodium gets rid of that electron, it's positive, chlorine is negative, and they stick together. So I draw a final structure with the positive charge, the negative charge, no dots on sodium, it's quote-unquote naked, even though we know it actually has a full outer ring, and chlorine gets all 8 dots to show that it gained 1. Let's try the same thing with calcium oxide. So we have calcium with oxygen. Calcium has 2 valence electrons and oxygen has 6. So I see that this dot could go here. There's an empty position, and then there's another dot. So calcium's not happy, but neither is oxygen. So what if we put that other dot here? What if they shared 2 electrons? So I draw my arrow to kind of show some separation. Calcium, when it gives away those 2 dots, it's going to form a +2 charge, right? Gets rid of 2. We put our oxygen now with all 8 dots in the brackets. Oxygen in this situation gained 2 electrons, so it has a -2 charge. So we're showing that attraction, that they're stuck together because of the positive and the negative. And notice these should cancel each other out, +2 and -2, because when they are bonded, it's neutral. Last one here, magnesium bromide, is magnesium bonded with bromine. Magnesium has 2 valence electrons, bromine has 7. So I see right away I can put 1 right there, and now we're in trouble, right? Magnesium is not happy. It still has that dot, that electron, but this bromine is fine. So the nice part is you can draw as many as you need. I always start with 1 of each because I don't want to confuse myself, but I notice bromine is happy here. Magnesium is not, so what if I draw another bromine? Well, bromine always has 7 valence electrons. Now, can that magnesium give away the dot? Yep, right there. So the only difference, everything's the same, but in order to show that I needed 2 bromines to make this work, I do my Mg, this magnesium gave away 2. I do bromine with all 8 dots, and I'm going to put a big 2 in front of the bromine to indicate that it took 2 bromines to cancel this out. For the charge, we still use the charge from the periodic table, or I just look at 1 of the bromines. What did this bromine do? It gained 1 electron. So bromine is -1. Do my charges cancel? Well, yeah, because this is +2, this is -1, but I have 2 of those bromines. So since each bromine is -1, it cancels out that +2. So again, it should look exactly the same. You get the charges from the periodic table or based off how many electrons were gained by that atom. The only difference is I put a big number in front for how many I had to draw. If I had to draw 2 or 3 magnesiums, I would put a number in front of magnesium. Hope that helps.